just in case you have been skipping around a little bit in the videos, I want to come back to two really important points for Gaussian surfaces that were introduced in an earlier section of this chapter. First, Gaussian surfaces must be closed. There is a well-defined inside and well-defined outside. And since how we use these words in English are sometimes not the same way this means mathematically, I talked about the Gerbil test. So if I have a coffee cup, I might colloquially talk about the inside or outside of the coffee cup, but from a mathematical point, it does not have a well-defined inside and outside. If I put a gerbil in my coffee cup, it can escape. On the other hand, if I have a box, a solid box that is completely closed, the gerbil can't get out from the inside of the box. So make sure you understand that it has to have a well-defined inside and outside. Second, when we're talking about Gaussian surfaces, they're just imaginary. They're a mathematical technique that we are using where we pick whatever shape we want. And so soon we are going to be talking about why we want certain shapes rather than others. So before, we were talking about the flux through a surface, and that's still valid. We can do that. But what's interesting and what's going to be useful is to talk about the flux through a closed surface. So recognize that when you're doing a calculation, like you might have a mastering physics problem, that does ask you to do the flux through some sort of arbitrary surface that is not closed. That's valid. That's okay. But we're moving towards Gauss's law, and Gauss's law always is interested in closed surfaces. So that's what's happening here. So you see that our integration sign has gone from having surf on the bottom, which, doesn't mean like wave surfing. That just meant surface, right? Surface. And now we have that little circle, which means the surface is closed, that you always are coming back to your initial starting point. So that's all that means. So the circle here implies a closed surface. So in this case, we now are going to have a sign convention, or a directional convention, if you will, for our A vector, or our little dA vector. So before we said that there's kind of like a little bit of an ambiguity. Now, if I have some sort of surface that's, closed and curvy, I'm not very good at drawing, and I think about some little section of it, and I want to draw my dA vector, it needs to point towards the outside. That's my dA. You don't want to have it pointing towards the inside, right? If I imagine looking at a sphere, dA needs to point out. It needs to not point in. And this is really just a convention, but again, all of our equations assume this convention. And what this means is that when you end up with negative flux, that means you have flux in. And if you have positive flux, that means flux out. And so, for instance, if we have our electric field coming out this way, this would be positive flux. That's not what I mean to do. That would be positive flux. So that's why the sign convention now matters. Again, if you don't have a closed surface, it's ambiguous, but we here are going to always work with closed surfaces. So now we are starting to move into Gauss's law, again, very, very slowly, because there's many big abstract ideas here we have to talk about first. So here's the tactic. And again, we haven't really talked about why you want to do this yet, but we're getting there soon, I promise. You need to choose a Gaussian surface. Again, it's imaginary. You get to pick whatever you want it to be. However, there are some choices that are going to be terrible, that aren't helpful. So what you want to do is have pieces, and maybe you get to have one big piece, that's clever, where each piece is either everywhere tangent to the field and or everywhere perpendicular to the field. And remember, those were our two simplifying cases that we actually know how to do the surface integral really easily then. So first you are choosing, right? And notice, this is you. Like, maybe you'll be given a hint. Maybe the problem will say, hey, this is the Gaussian surface you should use. But usually, you need to choose it. And so then notice that when you're choosing the surface, that needs to be tangent or parallel to the electric field. Now, the irony here, if you will, is that sometimes you're using this to actually calculate what the electric field is. So if you don't already know what the electric field is, how can you do this? The answer is symmetry. So I'm going to keep coming back to this, but the reason that this chapter started with symmetry, and there were a number of videos on it, is because symmetry is what allows you to have some idea of what's going on before you even do the calculation. Then we are using the previous tactics box, which was again perpendicular or tangent, gave you 0, parallel, where again this is between your area vector and your electric field vector. Perpendicular gave you 0, parallel gave you EA. So that's all tactics box did. So then you add up the results if you have multiple pieces, and you've now found your flux through a closed surface. The reason we are going to do that is Gauss's law, which is the next section.